The first question on module 4 is pretty simple. It says which one of the following substances should exhibit hydrogen bonding in the liquid state, right? So remember, in order to have a hydrogen bond, you need to have fun, right? Right, okay. So you need a hydrogen covalently bonded to fun, right? Either one of these. And then it's gonna hydrogen bond to fun. Okay, yes, okay. That's the criteria for it, right? In the options that you're given, does any one of them contain fun? Either fluorine, oxygen, or nitrogen? D, right, which is ammonia. So ammonia can hydrogen bond to other ammonias because one, this nitrogen is covalently bonded to an H, right? And another H from another ammonia can bond to the lone pair here. Okay, that's the gist of it. So ammonia should be your answer because it contains hydrogen, which is already bonded to an H. Okay, cool. Where's my eraser? Oh, it's right here. Okay. Okay. Cool. So then the next one says, which one of the following substances should exhibit hydrogen bonding? Right. It's the same question, but now we're given more complex molecules. Right. So still the same idea of fun. Right. So we need an H covalently bonded to either fluorine, oxygen, or nitrogen. And then a fluorine, oxygen, or nitrogen can hydrogen bond to one of those. Okay. So then which one did you guys pick? For 2, yes. I think A. A, okay. So A is CH3 and H2. Yes. So if we were to expand this molecule, we'd get something like this, right? And then there's 2 hydrogens here. Yes. Could there be a hydrogen bond here in this molecule? Yes, right? Because you have the nitrogen covalently bonded to an H, right? Now, the other option that you could have picked, right, is E, because you have oxygen in there, right? But the thing about E is that oxygen is not bonded to any H's. So you have CH3O CH3, right? This oxygen is not bonded to any H's, so there you can have a hydrogen bond. Remember, one of the criteria is to have a covalent bond for an H, right? So then if we were to expand this, we'd have something like this. Yes. So even though, yes, we do have lone pairs, there's no covalent bond to an H. It's C. Yes. Any questions so far? No? Okay. Cool. All right. So then the next one says, nitrogen molecules weakly attract other nitrogen molecules through what? What'd you guys get? You put D, dispersion forces. Does everybody agree? Or what else did you guys pick? Because what it's saying is, okay, you have a nitrogen, right? So nitrogen is a diatomic, right? And we're saying single molecules. So the Lewis structure would look something like this, right? Is this polar? Is this polar? Is this a polar molecule? No. No. Diatomics are not polar, right? So you can't have dipole, okay? Could you hydrogen bond? No, right? Because you need an H to hydrogen bond, right? Could you have an ion dipole?
Equal third, it would be neutral.
Right. Diatomics are non-polar, right? So diatomics wouldn't have a dipole moment at all, and you don't have any ions, right? And then nitrogen bonding, that's just not a thing. So then it's dispersion forces, right? That's the only force that's present in everything. Yes. Okay. Okay. Okay, the next one says, which of the following would you expect to have the highest vapor pressure at room temperature? What do you guys think? Right, you put E? Okay, why E?
Because it has the temperature closest, or the boiling point closest to room temperature.
Not necessarily. It is E, but not for that reason.
They're easier to break.
They're easier to, yeah, you need a lower temperature to break the bonds, right? Like you don't need such a high temperature to break the intermolecular forces, right? So because methanol is the lowest temperature there, you don't need that much temperature to break the forces. Yes. Also remember that the weakest force that you can have is London dispersion, right? If you have a molecule that's all London dispersion, it's going to have a low boiling point, but a really high vapor pressure. Okay, so low boiling point constitutes high vapor pressure. Does that make sense? Yes, no, yes, maybe. Okay, cool. So yeah, it would be methanol because it has a low boiling point. So you don't need that much energy to break the forces. Yes. Okay. So then number five is tricky. It tricked me. But so it's saying calculate the amount of heat needed to melt 2 kilograms of iron at its melting point, which is 1,809 Kelvin, given that the heat of fusion is 13.80 kilojoules per mole, right? So we're given a heat of fusion, which is 13.80 kilojoules per mole, right? We're given a mass, which is 2 kilos. And then we're also given a temperature, right? We're given temp 1809 Kelvin, right? Okay. So then, do you guys remember heating curves? The heating curves, right? Where it goes like this, solid, and then solid liquid, and then liquid. Yes. So it's basically that problem, except we're not given specific heats, right? We're not given anything else. So remember, for these types of graphs, it's temperature at the bottom, temp, and then, or actually no, it's time. Time at the bottom, and then temp. Yeah. So then we have something like this. Yes. This slant right here would be solid. This slant right here, or this, how do I say it? This flat surface would be solid to liquid, right? And then here would be liquid. And then here would be liquid to gas. And then here will be gas. Yes. Do you guys remember the formulas that you need for each of the slides? No.
I've forgotten the
MSAT. Yes. So for these slopes right here, it's Q is equal to MSAT. And then same thing here. Okay. So for these slopes right here, even here, Q is equal to MSAT. Yes. Okay. What about these flats, flat surfaces? What's the formula for those?
Q and That was,
Yeah, delta H, right? So they have different names. So then this is N. This one's fusion. This is, what is this H?
vaporization.
Mm-hmm. Is it VAP? HVAP, yes. Okay. Sorry. Okay. So we're given the heat of fusion, right? This is H fused, right? Okay. We are given a mass and we're given temperature. What would we do? What do we have to do?
You could equate.
What do you mean?
Will we change the mass to grams to get more?
We could do that, yeah. We could change this mass to what? What is 2 kilos in grams? 2,000, right? So you have 2,000 grams of iron, right? So it was Fe. Okay. So we have grams. You said we can find moles, right? So how do I find moles?
You did by
Molar mass. What's the molar mass of iron?
5.8.
You said 55.85? Okay. This is grams per mole. There's 1 mole. And this is grams. What do you guys get when you do that?
35.81.
35.81 moles Fe. Supposed to be a phone. 35.81 moles. Okay. Now what do we do with the moles?
Multiply by the delta H fusion.
Right. So in reality, most of these problems, right, you have to do this Q and then this other Q and then this other Q, right? But the thing is that this problem tells you that it's already at its melting point, right? It's not below any other point. The melting point is right here. Yes. So we can ignore this equation here. Yes. And then the amount of heat. So yeah, so we would just have the melting point, right? We can ignore this slope right here too. Because it just wants the melting point, right? It just wants this much heat to melt it. Remember, melting is solid to liquid. So yeah. So we would just use this equation. Okay. So then it'll be Q is equal to 35.81 moles of E times our heat of fusion, which is 13.80 joule. Yes. So then what do you guys get when you solve for that?
494.
494, right? What? Kilojoules, right? Because in this process, this moles and this moles cancel out, so you'll be left with kilojoules. So your answer should be okay. Yes. Does that make sense for everybody? Yes. Okay. Cool. May I erase it? Okay. So yeah, you gotta watch out for little things like that. When it says melting point, you want to only focus where it's already melting. You don't need the other formulas. Okay. So then the next one says, which one of the following liquids could have the highest boiling point temperature? Okay. What'd you guys put for that one?
It's the E.
E? Everybody put E? Yes. Not really. It's based on mass, but it's also based on the forces, the intermolecular forces that they can have, right? the more O's and H's that you could have in a molecule dictates the stronger force. Yes, and thus a higher boiling point because it takes more energy to break those bonds. Okay, so then in this case, it would be E because you have O's covalently bonded to H's. You have two, right? C is also a strong contender, but you only have one O, right? So you can only have like one intermolecular force between two of them. Does that make sense? Yes.
Can you say that again?
Okay, so a high boiling point, right? It often means more intermolecular forces, right? A hydrogen bond is the strongest intermolecular force, right, that you can have. So if hydrogen bonding is possible in a molecule, then it has a high boiling point. Yes, that's basically the gist of it. So so it couldn't be A, right? Because you don't have an oxygen bonded to an H. It couldn't be B because you don't have fun, right? C is a strong contender, right? It would be the highest boiling point if E wasn't an option. Yes. Okay. That's basically it. It should be E. How many questions? Two more. You just want to go over these two more questions and then you guys work on module 5 for yourself? Okay, cool. It says, which of the responses includes all of the following that can form hydrogen bonds with water molecules? Okay, so you're given option 1, which is sodium. Option 2, which is it's acetic acid. And it's 3, which is C2. It's 6. And then it's 4. CH3. Okay. So if we have water, right? Which one of these can hydrogen bond to water?
Acetic acid.
Acetic acid, right? Because you have this bond right here. So that's an option. And then who else?
I don't know what that is.
4. Yeah, I don't know what that is either. But yeah, it's 4, right? Because you have this N bonded to an H. Do you guys see that? Right? It wouldn't be 3 because you don't have FON. And then sodium by itself can't hydrogen bond because it doesn't have a hydrogen. Does that make sense? Okay, so it should be 2 and 4, which is option D. Yes? Cool beans? Okay. Okay, last one from this module. Do you guys feel good so far about module 4? Okay, cool. So it's 30 here, 20 here, 10 right here, and then it's 40, 50, 60. Okay. So then this one is asking sublimation of substance X is likely to occur at. So what is sublimation? Solid to gas, right? If this area right here is solid, this one's liquid and this one's gas. The sublimation would happen at around here, right? Before the triple point. Yes? Okay. So with that in mind, where would it make the most sense? At what temperature? 20, right? At about 20 degrees Celsius. So right here. Yes? Does that make sense? That's basically the question. So it's just terminology, sublimation, deposition, whatever. Cool. Cool. So then module 5, work on it by yourselves. And then I'll give y'all 15 minutes. So at 3:35. Yes. Okay. Okay, let's go over. Question 1, module 5. It's asking what is the osmotic pressure of a solution that contains 13.7 grams of propyl alcohol dissolved in enough water to make 500 mils of solution at 27 C. Right. Okay. So then what's my equation for osmotic pressure?
Pi equals I.
I mark, right? Where T is our temperature, R is our constant, and M is molarity. Yes. Okay. And I is our Van Hoft, right? So, what's my rate? What's the value of my rate?
0,
2:1. Yes. Units.
This year for
Yes. Over K, right? Okay. Yes. Okay. And then our T has to be in Kelvin. Yes. Okay. So then what's 27 degrees in Kelvin? Just 300? Oh yeah. 0.50. Yeah. Okay. Kelvin. Right. Okay. So this is RT and then molarity. Are we given molarity? No. But can we find it? Yeah. So remember, molarity is moles of solute over, oh my God. Yes, liters of solute. Yes. Are we given liters of solution? You given milliliters, but you can convert to liters, right? So 500 mils in liters is just 0.5, right? And then our moles of solute, right? So are we given moles? No, but we can solve for it, right? It's given grams, and then it's given us our formula, which we can find moles, right? We can find the molar mass from the formula. So it's 13.7 grams of C3H2, C3H2OH, right?
That's
Oh, whoops. Okay. Yes, C3H7OH. Okay. So then to convert to moles, I need the molar mass. The molar mass, which is C times 3, H times 8, and then it's just 16. H is 1.008, and then this is 0.01. So I'll get 36.06. No, 03. Whoops. I'll get 8.064. And then well, I'll just get 16. Right. What do you get when you add all this up? What do you get? 60? 0.97 grams per mole, right? So this is our molar mass. So to convert grams to moles, grams, we just divide by our molar mass. One more. What do you guys get when you divide 13.7 by that? 0.2247. Did everybody else get that? Yes. 0.2247. Okay, cool. So then we have our moles. Moles, right? Okay, so 0.2247 divided by 0.5. 0.4494. Did everybody get that? Did you? Yeah. Okay. Let me just check. You guys don't sound too sure.
I got 0.45, but I got different.
0.45?
But well, I got 0.22, but I got different for reference.
Oh, you put this? Did you do that or no?
I put different.
4494. That's what I did.
4494. Just as long as you get, I guess, 0.45, you're fine. Yes, there's something close to it. Okay, cool. This is molar. Okay, so we have our molar. Yes. 0.45 molar. Okay. Now, what's our ventile?
1.
1, right? Because it's all covalent bond. You won't have any splitting. It's not ionic. When you have ionic bonds, when you have electrolytes, we'll go over a question right now that goes over that. Okay. So all you do is just multiply all that good stuff. Then you should get osmotic pressure in atmospheres. Yes, so it's 0.45 times 0.0821 times 300.15. Did you guys get it? Yeah, 11.2. I got 11.1. Yeah, it could be a rounding error. Right. So our answer should be E.
Yeah.
Yes.
Sorry, I just went straight to like I got the molar mass and that's what I
See.
That was bad too, and it like I line it next to that, and I was like, wait,
that's
Okay. Okay, but is it clear? Yes. Okay. Can I erase it? Okay. Okay. So then, number 2 says the vapor pressure of water at 20 degrees Celsius is 17.5 millimeters of mercury. What is the vapor pressure of water at 20 degrees above a solution prepared from 200 grams of sucrose and 350 grams of water? So what equation would we use for this one? Number 2. So we have a solvent, right? We have water, right? And it's given us the vapor pressure, right? Yes, the vapor pressure of water at a certain temperature. Yes? Okay, it's asking how would that pressure change if we add sucrose into it, right? So then what equation would we use? It's a law, okay? It's Raoult's law, right? What's Raoult's law? X, okay, X of A, okay? E naught, right? This naught means initial, right? So we want the pressure initially, and then what does this X stand for?
Oh, the mole fraction?
Mole fraction, right? So then our mole fraction is moles of A over total moles. Yes? Okay. So then are we given an initial pressure?
I know the initial, but what's that other?
Oh, sorry. I meant to do an arrow.
Oh.
Not okay. Um, are we given an initial pressure? Are we not?
Is the 1.86? Wait, I'm looking at 3. What am I doing?
It's 2. 17.5. It's okay. Right? Because remember, Raoult's law says, okay, this is our initial pressure. What would happen if we added a solute to it, to our solvent, right? So this is the pressure of water. So the mole fraction that we're going to have to do is for the moles of water, right? Okay. So we're given 350 grams of water. Obviously, we need moles of water, right? So we divide by 18, which is our molar mass. And then sucrose, we're given what, 250? No, 200. Just 200 grams. One more. And then you got to find the molar mass of sucrose. So it's CHO. Yeah. C12, H22, O. My God. 11. Yes. 11. So that's C12.01. H is 1.008. And then O is 16, right? So this would be 144.12. Yes. And then this one would be 22. 176.
Yes.
Okay. And then oxygen would be 176. Okay. Cool. So now what do you do? What do you get when you add that up?
342.
296. So then we put this over here. Yes. Okay, so we just take the mass of sucrose, we divide it by the molar mass to get our moles. Okay. So what do you guys get when you divide? Yeah, 200 by the molar mass. Or, oh, 0.58. Did everybody get that? Yes? What about water?
19.4.
19.4? Okay, cool. Moles. Okay, now we can do our mole fraction, right? We have all our moles. So the moles of A would be the pressure, would be the water, right? Because we got the pressure of water, which we're going to treat as our A because it's our solvent, right? So we're going to put the moles of A, which is the moles in respect to water, over the total moles, which how do I get total moles? You just add, right? So it's 19.98, right? So then what do you get when you do that?
0.97.
0.97? Okay. Right. Okay. So then I'm gonna write it over here. .97, right, times our initial pressure, which is 17.5. Okay. So what do you guys get when you do that?
15.8.
0.98. What?
Oh, I forget what you call that.
It's,
Something in the middle.
yeah, millimeters.
Put that round to 17 or would we put 16?
Yeah, it rounds to 17. Yeah. Cool. Cool beans. Cool.
Are you supposed to send the workshops?
Yeah, in the workshop Blackboard. Cool. Number 3, I actually don't like. So I was doing this right before to make sure that, I got the answers. But number 3 really confused me. We can go over it, right? If you want to. You want to go over it? Okay. So it says a solution that contains 55 grams of ascorbic acid, vitamin C, and 250 grams of water freezes at, is that negative? Negative 2.34. Calculate the molar mass in units of grams per mole of the solute. Like kf of water is 1.86. Yes. Okay. So then again, we want to find a freezing point, right? What formula would we use? Well, we want to find molar mass given a freezing point. What formula would we use?
Was that the way you use the modifiers?
Yes. What formula is that? What do I write? What do I write? Well, it would be, yeah, okay. It's the freezing point modifier. The freezing point depression, right? Okay. So it's delta T negative I kf molality. Yes. Okay. Yes. That's a constant that you're given. That's the freezing point of whatever.
For the boiling point, maybe K.
Yes, kV, and then this is positive. Yes. So delta T, right? Usually in physics and math, delta T expands to final minus initial. So it expands to final minus initial, right? And in this case, we're talking about solutions. So our final will become solution, right? And our initial would become solvent. Yes, because initially we would have a solvent, right? If we add a solute to it, we would have a solution. Does that make sense? Okay. So negative I K mol. Yes. Okay. So now if we wanted to solve for our solution, we'd have C solvent minus I K F A M. Yes. You guys see how I got there? I just added this, moved it to the side. Okay, cool. So the T's are the freezing points, right? Are we given a freezing point for the solution?
Yes.
Yes, right? What is it?
Negative 2.34.
2.34. Okay. And then our solvent in this case, it'll be Celsius. Yeah, that's fine. Okay. So then what's the freezing point of our solvent?
1.8.
Ooh, no. So what's our solvent in this case?
The ascorbic acid
That's a solute, right?
water.
It's the water, right? Do you guys see how it's the water? Because we're adding the vitamin C to the water, okay? So the vitamin C would become our solute, okay? So then the freezing point of water is?
0.
0.
You're all set.
Right. So then, what's our Van Hoff for water?
One.
One. Okay, our KF,
Is 1.86.
1.86, right? What's the units?
Celsius over
Molal. Yes. Okay, and then are we given molality?
no.
No, right? But what is molality? What's our formula?
Those are solid
Uh-huh.
over kilograms.
Kilograms of solvent, right? Okay. Do we have solvents? Do we have a solvent?
Water.
Water, right? Do we have a mass for water? Yes. Right, what is it?
50 grams.
250?
Yeah.
Okay, what would it be in kilos?
0.25.
0.25, right? Okay. So now the question, right, is asking for the molar mass. We have every single variable but our molar mass, right? And we need the molar mass to find the moles of solute.
Yeah, so we
So-
use the moles to get the mole.
Well, we can't have moles, right? Because we need the molar mass. We don't know what the formula for.
In there. And we solve for moles.
Yeah.
Uh,
So we wouldn't treat this as X. That's why I don't like this question. But we wouldn't treat this as X. We would treat this as, well, okay, what's the mass of our solute?
55 grams.
55 grams, right? How do I get to moles?
We divide that by one.
We divide that by the molar mass that we don't have, right? So you would just plug this in here. And we would treat that as X, right? So basically what we have to do is expand this. So it's gonna be, so when you're dividing by a fraction, right, it's keep, flip, change, right? KFC. So then it's 55, right? We keep this, and then our X, molar mass, and then we flip, right? That division turns into multiplication, right? Times, we flip it, right? So it was 25 grams, no, 0.25. Yeah, you flip it, right? Because it was 0.25 over 1. We flip it, now it's 1 over 0.25 kilos. And at this point, we just solve for X. Does that make sense? Yes? Okay. So then 0 minus 1 is negative 1? Am I wrong? Yeah. Whoops. 0 minus, so we have negative 1, right? But we can just have negative 1.86, right? And then we have our 55 grams over X. And then we have 1,250. Yes, and then this is equal to that, to the negative 2.34, right? So we have to move X. Okay. So I guess what we can do is just divide, right? We can divide by negative 1.86. So then it'll be 2.34 negative divided by 1.86 negative, which is 1.26, right? This is, well, this is degrees Celsius. No, this is degrees Celsius. This is degrees Celsius over molal. So this would be 1. That would be kilograms over molal, right? Equal to, how should I do this? I'm gonna erase it. Okay, well, I'm gonna erase it here and then do it here. So it was 1.26 kilograms over yields 55 over x. And then another 0.25, right? Well, we would divide by 1 over 0.250. 250. And so these, we would get so then it's 1.26 divided by 4. Equal to 55 over x, which would be the same thing as saying x is equal to 55 over 0.350. Yeah. Is that a choice? Yeah, it's D.
I like that problem.
You like it? I don't. There's a lot of going back and forth. Right. Okay, so basically all we did was just plug in everything. And then our missing variable was the molar mass, right? And then we substituted most of solute by 55 over x, which we're trying to find x, right? We expanded the formula of molality, right? So we get 55 over x times 1 over 0.250, right? Okay. And then we just simplified everything else and we left x by itself. Pretty simple. No, right? I had a hard time with it. But yeah. Does it make sense though? Okay.
Please, you can look that up. I don't know if I can put that up on my phone though.
Okay.
But like the math part?
Okay. Yeah, it's just the setup.
I look at you.
You just have to know what it's talking about. Okay. 4. This is an easy one. Now, says how many grams of water are needed to dissolve 27.8 grams of ammonium nitrate in order to prepare a 0.52 ammonium nitrate solution? Oh, and that's molar, right?
Yeah.
Okay. So what's my equation for molality again? Yes. Okay. Am I given a molality?
Yes.
Yes, right? What is it?
452.
452. Molar is equal to moles of solute and kilograms of solvent, right? In this case, our water will be our solvent, okay? And then our ammonium nitrate would be our solute, yes, because we're given the molality for ammonium nitrate.
So the grams become the moles.
Yes, exactly. So then it's 27.8 grams. Ooh, it's getting dusty in here. Okay, it's let me see. It's NH4NO3. So then it's NH4 NO3. Oxygen, which would be times 3 times 16. This would be 1.008. And then this would be times 2, right? Times 14.01. Okay. So then here we'll get 48. Here we'll get 4.0. Oh my God. 32, right? And it's 28.02. What do you get when you add that up?
80.0.
0.052. Okay. So then that's our molar mass. That's one more. One more. This gives you 27.8 divided by 80.052. 0.35 thermals. So our moles of solute would be 0.35 over our kilograms of solvent, which is what we're trying to get to, right? Right. So we just solve for x. In this case, x is kilograms of solvent. So then it'll be Kg, or I just x, is equal to 0.35 over 0.452. Yes. Okay. What do you guys got?
0.77.
0.77, right? But remember, this is in kilograms. Is it 1 in grams?
Yes.
Right. So then we just expand this, right? What's 0.77 kilos in grams?
770.
Right, 770, which is choice
C.
C, right? Basically rounds off to this. Pretty easy, pretty hard, pretty okay. Does it make sense? Right, where we given molality, and then we found molality through its equation. Yes. Does it make sense? No questions? Cool. Cool beans, cool beans, cool beans. Okay. Do you guys want to work on it by yourself again, or do you want to move on to module 6, module 7?
Yeah.
Up to y'all. Look at the rest of the questions. Tell me.
Is there gonna be an answer key?
An answer key? Yes, there is. Yeah, I'll post it. I'll post it. Yeah,
In case we don't get to it.
that's all of it. Yeah.
Oh, can you go over number 10, module 5?
Which one of module 5? It's the same one. It's the same question. Okay, so it says when 24 grams of a non-electrolyte XX are dissolved in 500 grams of water, the solution has a freezing point of negative 0.47 degrees Celsius. What is the molar mass of non-electrolyte? K of water is 1.86. So it's the whole thing, right? So it's T of solution, right, is equal to T of solvent minus IKF M, right? So what's the temperature, the freezing temperature of solution?
Negative 4.47.
Yes. And then the freezing point of our solvent, which is water,
Yeah.
0. Yes. So we're told that's a non-electrolyte, right? Because it's a non-electrolyte, it doesn't break apart, right? So its I factor would just be 1. Yes. Okay. KF
1.86.
1.86. Okay. And now molality, right? Remember molality is kilograms. It's molten solute over kilograms of solvent, right? We are given a solvent. We're given, well, let me write it actually. Kilograms. Same deal, right? It'll be, are we given a mass for the non-electrolyte? Yeah, 24 grams, right? So again, we're solving for molar mass, so it'll be 24 over molar mass, which I'll just treat as X, right? Over kilograms of solvent, right? 500 grams into kilograms is 0.5 kilos, right? So then we just expand this, we simplify this. So again, it's negative 1.86 degrees Celsius times kilogram over moles. And then we expand this to say 24 over X and then 1 over 0.5. Right? This is negative, and then is equal to negative 0.17. Okay. Now we just solve for it, right? So then it's, we divide by, just to get rid of it. So then it's 0.47 negative divided by 0.6 negative. So here I get 0.25. Going to be 24x. I'm going to divide here by 1 over 0.5. 1 over 0.5 is 2. So 0.25 divided by 2. Sorry if I'm going over this kind of quickly, just because it's the same thing as the last problem. And then x would equal 24 over 0.125. Yes. So that's 24 divided by 0.125, which is 192. And option. Well, it's 190. Yeah, yeah, it'll be E. Huh? Yeah, it's close enough. Let me actually go to the key.
Actually, I know they're a little different. I got 189.
Okay, well, that's fine. That's closer, actually. Sorry if I went over this one kind of fast. Is that okay? But you get the process, right? Okay. Any other questions that you guys want to go over? Yes, no, yes. Oh my God.
You already work all of these out?
Yeah.
Because if anything, you can post the key and we can try to do it, and if we fail, like, we can try to.
Right. I mean, the point of the video is just to work them out, right? Because the key just has the answers.
Oh,
But-
I don't think he has the word.
No,
It's like,
yeah. But the point of the review is to work them out in the video.
I don't think he had the word, so I was like, so we can see where we went wrong, but.
No. Okay. Anything else? Module 6, do you guys want to go over that? Because question 10 and 11, we've already gone over Raoult's law. We already worked one where we solved for molar mass, right? Do you guys want to do 9 or no? I mean, are you guys okay finding molality given molarity and density? Yes? Okay. So do you guys want to move on to module 6? Yes? Yes? Okay. So let's do number 1 on module 6. Okay. Or do you guys want to work on module 6 by yourself and then I work on it later? With me? Okay, cool. Okay. So it says ammonium ion reacts with nitrate ion to yield nitrogen gas and liquid water. The following initial rates of reaction have been measured for the given reactant concentrations, which in the following is the rate law, the rate equation for this reaction. Cool. So what's a typical rate law look like? Bye, have a good one. Okay. Thanks. Have a good one.
Where it's like rate equals then A to whatever order it is.
Uh-huh.
And
So we're just gonna treat them as X and Y. Am I missing anything? Okay, right? Okay. Oh, I know it looks ugly. My apologies. Okay, cool. So our rate is equal to our constant times the concentration of A at a certain order, then concentration of B at a certain order, right? The only possible way to know orders is to do experiments, right? So then, in questions like these, we're given a graph, a table, sorry. So where it gives us different experiments, right? So this one gives us experiment 1, 2, and 3, right? One is for ammonium, another one is for nitrite, and then another one is for our rate, measured in molar per hour. Cool. Cool. Okay. So here we're given 0.010. The next one is what?
0.015.
Next one,
0.030.
30. Okay, what about this one?
0.020.
Okay.
0.020. And 0.010.
Okay. And then the rates?
0.020.
Oh my God. Okay.
0.030.
Okay.
0.015.
So how do we find rate? How do we find order? Sorry.
When the other is held constant.
Right. We need one to be held constant and the other one to change. And then we can compare the change in whatever reactant we're looking at and the change in the rate, right? To see how the change in this affects the rate. Yes? Okay. So let's go ahead and find ammonia. Yes, when nitrite is held constant. Okay. So do you guys want to do experiment 2/1? Yes. Okay. So then let's do experiments 2/1. So then it'll be 0.015 over 0.010. Gives you what?
15.
15? Really?
1.5.
1.5, right? I think that's what I got. Yeah.
Yeah.
You want to check your math? Okay. Yeah, it should be small numbers too.
Make it 0.010.
Okay, no, it's okay. Okay, so 1.5, right? So then since we did 2/1, we have to do the same with our rate, right? We'll do 2/1. So then it's 0.030 over 0.020 gives you 1.5, right? So because these two are equal, what can we assume the order is? first order, right? Because it affects the rate proportionally, right? We changed 1.5 in molarity, and the rate changed in 1.5. Yes. So to write a rate law, it would be rate is equal to K, right? Which we don't know. And then ammonium, first order, which we just found out, right? And then nitrate, which we still don't know. Okay. So then how would I find the rate or the order for nitrate? When ammonium is held constant, right? But the issue is that ammonium is not held constant in this problem. Okay. So what we have to do is kind of do a makeshift rate law, right? Where we compare the changes, okay, in each one. Okay, so it'll make sense if I go through it, okay? So let's pick experiments where nitrite changes, right? And even though ammonium still changes, well, we want to see how nitrite changes, okay? So let's do 2/3. So then it'll be 0.020 over 0.010, right? Which gives you 2. Okay. So then now let's do the same for our rate. So we did 2/3. So then let's do 2/3 again. So it'll be 0.030 over 0.015, which is a change of 2. Right. Okay. So we would say that it's first order, but ammonium is changing, right? So the same way, let's do 2/3. Okay, the same way you did for nitrate. So it'll be 0.015 over 0.030, which gives you 0.5. Okay, cool. So we have the changes in each, okay? But what I meant by makeshift rate law is basically just have the change in concentration of both, right? So for ammonium, sorry, it's a change of 0.5, right? Because we did experiments 2 and 3, okay? And do we know the order for ammonium? We do, right? We found it, first order, okay? Now let's do the change in nitrite. By how much did it change? 2, right? So 2, but we don't know the order, okay? And now how much did our experiment change? 2, okay. So now all we have to do is solve for x. Well, technically solve for x, okay? Since we know that ammonium is first order, well, 0.5 is just gonna be 0.5, right? So then we want to leave this rate by itself, okay? And we're gonna treat it as x. So we would just divide by 0.5, right, to leave this by itself. And then it will be 2/0.5, which is 4, right? Two to what power it gives us 4? 2. So then we know that our order has to be 2. So then nitrite is second order, ammonium is first order. Did I go too fast?
No.
No? Did it make sense? Yes. Right. So you want to do like a makeshift rate law, right? Where you have the orders of the knowns, right? So we found the order of ammonium. And then you want to do the changes. Okay, do the changes of each. Ammonium changed by 0.5. It's first order, so it's just going to stay as 0.5. And then nitrite changed by 2, but we don't know the order. Okay, and then our rate changed by 2. So then we would treat this as x, solve for x. We would divide the 0.5s and leave x by itself. So we get 2 to the order of x gives us 4. 2 to the second power gives us 4. Okay. So then, your rate law should be K ammonium first order and nitrite second order. Does that make sense? Yes. Okay. Can I erase it?
Yeah.
Cool. Cool beans, cool beans, cool beans. Any problem in specific that you guys want to go over? Or do you just want to go to the next one? Number 4? Okay. Okay, for the hypothetical reaction, okay, of A plus 3B yields C, 2C, 2C, right? The rate of appearance of C is given by the expression delta C over delta T, right? Okay, the quantity of delta C, delta T can be expressed as, okay. So basically we're just doing ratios, right? So do you remember your rate expressions? Yes? So what would the rate expression for this one be? For this whole reaction?
Negative delta A over delta.
Right?
Equals negative 1/3 delta B over delta C.
Okay.
Equals 1/2 delta C over delta.
Yes. Okay. So then all we have to do is just solve for C in the terms that the question gives us, right? We don't necessarily have to have a specific term that we're looking for. Let's just solve for delta C, okay, for in both terms, okay? So let's do it in terms of B. So then it's delta C positive 1/2 over delta T, right? This whole delta C over delta T, we're gonna treat it as X, okay? So then is equal to negative 1/3 delta B over delta T. And again, delta B over delta T, we're gonna treat as X, okay? So if we were to solve for delta C, we would divide, right? Because this is multiplying by 1/2. So let's divide by 1/2. Get rid of it. And again, we're dividing fractions. So it's keep. I'm just worried about the coefficient here. Okay, so it's keep, negative, flip, we're gonna multiply, and then change. So then it's 2 over 3. Yes. So then it's 1 times 2, which is 2, negative, right? And then 3 times 3. No, those stay the same, right? No, you multiply the 3 times 3, right? Or no? Oh my God. I should really go back. Oh no, it's not 3, it's 1. Oh my God, why didn't you guys say anything? Why didn't you guys say anything? Okay. Negative 2/3, right? And that's in terms of B. So we conclude that delta C over delta T is equal to negative 2/3 delta B over delta T. Is that an option? Yes, it's B. Does that make sense?
Yeah.
Yes. Okay. You guys should have said something.
was trying to figure out what was wrong.
Like, oh my God.
What's wrong with this picture? Okay. Okay. Any other question? Oh, damn. No. Yes, no, maybe.
Can we do that?
You want to do a graph? Yeah? Okay. Do you want to do the number one that's in there?
Yeah.
Okay, so module 7, number 1. So it says label everything appropriately, show linear increments along axes. The following gas phase reaction takes place inside a closed chamber. 3A plus B yields 2C. Yeah, okay. 2C, right? The initial concentrations are C initial is 0. Zero molar, right? And then A and B initial are 0.20, right? Molar. Yeah. Yes. Yes. Okay. The reaction is first order in A and zeroth in B. The rate constant in the rate equation for this first order reaction at a certain temperature is 3.46. So we're given a K, which is equal to 3.465, right? Times 10 to the negative 2 minutes minus. Okay. Determine the half time for this process at this temperature and use this information to show plots, yada, yada, yada. Cool. Okay. So we know that it's first in respect to A and 0 in respect to B. Okay. So what would I have to do first in order to plot this? The little chart, right? The little table. Oh my God. Okay. This is A, B, and C. And then this right here, giving you our half-life. Okay. So we would start at 0, right? And then I'm just gonna write the coefficients up here. Okay. So it's 3, 1, 2. Okay. So usually for these problems, they don't give you a half-life, right? Or anything to find a half-life. In that case, like in your homeworks, you would do 0, 1, 2, 3, right? But in this problem, they did give you something to find a half-life, right? Which is what? What does it give you to find a half-life? Well, okay, let me ask you this. What order is this reaction in?
First.
It's a first order reaction, right? Okay. Is there any first order equation that we could find a half-life for?
Oh.
You said that, oh, like, oh,
It's T 1/2 equals 11 kilojoules.
yes. Right? Because this is a first order reaction, we can use this equation to find our half-life, right? We are given a constant, which we can plug in here and solve for T half-time, okay? Like I said, usually, like in problems in your workbook, you just do increments of 1, right? So it's 0, 1, 2, 3, 4. But if they give you a constant, or an actual half-life, and you use that. Okay. So they give you a constant. So then it'll be the natural log of 2 over our constant, which is 3.465 times 10 to the negative 2, which gives us our half-life, which is 20. Will be 21 minutes, right? Because our constant dealt in minutes. Okay. Minutes. Okay. So our half-life would be in increments of 20 minutes. Okay. So I'm going to put 20 here. Yes. And then it's an increment of 20. So I'm going to do 40, 60, and 80. Okay. Like I keep saying, 5 of these is fine. Right? 5 of these plots. Oh, damn. It's fine. Okay. Because that's enough to show what is happening. Okay. So what do we need to do? What else do we need to do?
Well, we can fill.
We can fill A. How?
Gonna go down by half. So it'll be like 0.10
Right, but why A?
because it's in the first place.
It's the first order, right? So whatever's in first order would be our limiting reagent, or whatever is used up the most, the fastest would be our limiting reagent. Okay, so we would treat A as our limiting reagent, and the reason that we decrease by half is because a half-life is the time that it takes the limiting reagent to reduce by half, to deplete by half. Okay, so at each one of these points, it'll be half of the limiting reagent. So yes, you're right. So then it'll be 0.10 and then 0.05 molar, and then 0.0125. Am I right? Yes.
Yes.
Let me check.
No, it's 0.025, and then that one would be great.
Oh, okay. Whoops. Thank you. Okay. All right. So we have A. We already identified that A is our limiting reagent, and we know that A depletes 3 times faster than B. Okay. So then, how would I find B?
We would do a ratio.
A ratio, right? I'm gonna erase this right here. Okay, we can do a ratio, right? So remember, for the ratios, you want to take whatever concentration is at the time that you want, right? So we're gonna take the concentration of A at 20 minutes for B, okay? So then it'll be 0.10 molar A. What would go down here? 3A, right? Because we want to cancel out the A's. And then up here would be 1B. Yes? So you just divide 0.1 by 3, which would give you 0.03. Okay. Now, what do we do with this? We subtract it, right? Because what this ratio is saying, okay, this is how B is going to deplete. Okay. So that's 0.03. It's 17, right? Am I wrong? Am I right? Okay, cool. Okay. Now we just keep doing the same pattern as before. I don't know if the trick in the workbook works. Yeah, let's try it. So the trick is to divide this by 2. So it's 0.03 divided by 2, which is 0.015 molar. right? But if we actually did it, it'll be 0.05 molar divided by 3. 0.5 divided by 3. I mean, it's close enough, right? Because,
Say 154? Oh,
what do you mean?
no.
Oh,
That's next to the next one. 154.
154? Right.
That's what we gave. I don't know what it is.
Sorry, what do you mean? Like this right here?
0.154.
Hold on. Hold on. I got 0.155 or 1.54. You would get that, right? If you did this divided by 3, right? Or no?
No, you would do, wait, what?
You would do this, right? 0.05, and then you would do the ratio, right? Which would give you 0.016666. Continue, right? So it's 0.016 minus 0.17. I got 0.153, which is close enough. Again, like he's not a real stickler on like, oh, this is like the actual value that you're supposed to get. It's just to get a rough idea of how the graph is supposed to look like. Yes. Is that cool? So yeah, I mean, if I did the shortcut, I got 0.155, you got 0.154, and if we actually subtracted it by the ratio, I got 0.153. Close enough, right? Okay. So I don't really trust the shortcut, so let's just keep doing it this way. So then it's 0.025 divided by 3. Right, this minus 0.153. I got 0.145. Okay. And then last one would be 0.0125. So 0.0125 divided by 3, right, minus 0.145. I got around 0.141. Did you guys get that as well? Yes? Okay, cool. Cool. Now let's do C. Yes. So now our ratio is going to change. So we still want to deal with our limiting reagent, right? But now we want to do it in terms of C. So this top coefficient is going to change to 2C because that's what we want. And again, we still want to deal with A. So it'll be 0.10A times 2/3, 0.10 times 2 divided by 3, 0.06 forever. But now we add that, right? Because our products are forming 0.067. Okay. Same deal. 0.05 times 2 divided by 3, right? Plus 0.067 would give me around 10. Keep going back and forth. Whatever. 0.025 times 2 divided by 3. 0.016 plus 0.10. 0.12 molar. Okay. The last one should be. Yes. You guys see where I'm getting these values from? Yes. Okay. So in the end, I got around 0.1. Wow. Did you guys get something similar? Or exactly? Yes. No. Maybe. Yes. No. Yes.
It's close.
Yeah, like I said, it's close enough, right? You might have a few rounding errors, but it's just to get a rough idea of how the lines are going to act, right? So then let's get to the fun part, which is plotting. So remember, this graph is a concentration versus half-life, or this time graph. I know. We're almost done. Okay. Yeah. I mean, literally the first question of my exam was this. So what else? Okay. So we started at 0, right? Let's do, again, we want to have a nice even graph. So let's do this. You don't have to buy a ruler. I mean, just use your calculator. Everyone's doing it. Just kidding. I mean, you could buy a ruler. I mean, we'll let you. I don't see what's wrong with it. Cool. Now to decide what points to put, right? So our lowest point in this graph is 0.0125, right? So we want to see where our highest value is going to be, and then our lowest value. So for time's sake, I'm just gonna put 0.2 up here. I'm gonna erase these. 0.2 molar here, and then I'm gonna do well, 0.1. No, yeah, should I? Yeah, I should. Okay. 0.05. 0.25. Right. Okay. So then, both A and B start here. Let's plot A. So then A at half-life 20 was at 0.1. That's around right here. And then 40, it's at 0.05. So it's right here. All right, 60, it's 0.025. So it's right here. That was getting pretty steep. Okay, and then finally 0.012, which is half of this. Oops. Right, that's for A. Okay. Now for B, depletes slower, right? So instead of 0.1 at 20, it's 0.17, which is close to 0.2. So I'll just do it like right here. Here, let's graph over. Okay. So this is gonna be B. And then it's half of this at 40. So I'm gonna do half of this, more or less. And then a little bit under that at 60. So it's a pretty slow reaction. Look at my points. Cool. And then 80, we got around the same amount. So I'll just drop it a little bit. Yes, something like that, something similar. Okay, now for C, well, it's just the same thing, just that it starts from 0, and we just plot from there. Okay, so here at 20, I'm already at 0.067, so I'm already a little bit above here. All right. Okay, and then at 40, I'm at 0.1 here. I'm gonna do that. And then 0.12, which is a little above 0.1 at 60. And then 0.13, which is a little above 80. Yes. Something like that. Where it's clear that A depletes 3 times as fast and B 3 times slower. Okay. And C is produced 2 times as fast. Okay. So again, that's why I said that the points should not be that important, right? It's just to get the rough idea of where everything is. Does that make sense? Yeah, these problems take a long time, but it pays off, I guess. Like it's kind of satisfying to see this. I don't know. You could, I mean, just kidding. No, you can't. I was gonna say like you could just do that, but you could just draw it like whatever, but you can't. Yes, cool. Another problem that you guys want to go over? I know this one took a long time. Okay. Can I erase this one? Yeah. Did it make sense? Do you guys feel better about graphing?
Yeah.
Yes. Anything in specific that you want to go over? Number 5 and module 7? Okay. Ooh, it's one of these. Yes. Okay. Says it takes 42 minutes for the concentration of a reactant in the first order reaction to drop from 0.45 to 0.32 molar at 25 degrees Celsius. How long would it take for the reaction to be 90% complete? Okay. So it's a first order reaction, right? What formula would we use for first order?
The ln of a given time
Right.
equals -18
Right.
plus ln of the initial.
Yeah. Nice. Good job. Okay. Am I given? What am I given? Right. Okay. Let me go over each variable. Right. Like you said, this is A at a given time, right? After some time. This is K, which is constant all throughout. This is the time it takes to go from your initial concentration to your final. Okay. That's basically all it's saying. Right. So then, what do I have to do next? Find K, right? Because initially you're given final concentration and initial concentration, right? You're given a time, and the only missing variable is K. So we want to know what K is, right? With that, we can find how long it takes for a reaction to be 90% complete. Okay. So what are my values that I plug in? What would I put for here?
0.32.
That's my final. And then negative K, we already established that that's our missing variable. What about my time?
42 minutes.
42 minutes, right? And then what's my initial concentration?
0.35.
45, right? Initially. So, okay, cool. So all we have to do is just solve for K. Yes? Okay. So then the natural log of 0.32, I got negative 1.14 is equal to negative K times 42, right? And then the natural log of 0.45 is negative 0. Let's just do 8. Okay. So then to get K by itself, subtract here, minus. Okay. And then here it's minus, which is just at, right? So 1.14 negative plus 0.8 should give me 0.34, right? Negative K, 42. So then we divide by 42 to get rid of to get K by itself. This divided by 42 would be negative 8.1 times 10 to the negative 3 equal to negative K, right? I still have one more thing to do, which is just divide by negative 1 to get K by itself. And then our K would equal 8.1 times 10 to the negative 3. Yes? Okay. Cool. So we solved for our K given that reaction, right? And remember that our K is, well, a K is a constant, right? No matter at which reaction, at what point of the reaction, right, your K is always going to be the same. It's constantly going to be the same. Okay. So we have our K, which was missing, right? Now we need to solve for a reaction that's 90% complete, right? We need to find out, well, we want to find out how long it takes. It was 5, right? Yeah. Yeah, 90% complete. Okay. So we want to find time. It's still a first order reaction, right? So we would use the same formula. Ooh, getting dusty. Okay. We would use the same formula. But how would I solve it? How would I go about it? If a reaction is 90% complete, right? What can we assume?
We're looking for the 10%.
Yes, the remaining 0.10, right? The remaining 10%. We can assume 1 molar, right? As our total concentration, or sorry, initial, and then 90% of 1 molar. But it's already 90% complete. So we want the rest of the concentration. Does that make sense? Right? So 90% of 1 is just 0.90. And then 0.90 minus 1 is 0.10. So 0.10 initially. We have our K, right? But now our time is missing. I'm not even gonna, well, I'm gonna include it. But the natural log of 1 is just 0, right? So you don't even have to worry about this part. Yes? Does that make sense? Okay. So then Natural log of 0.10 is negative 2.3, and then it's equal to our K. T. So we want to find T, so we want to leave T by itself. So it's negative 8.1 times 10 to the negative 3, which would cancel this out. And then right, which would give us our T, which would be
280.
ooh, 283. Is that an option?
Oh, well, it's 0.95, so it would be.
Yeah, E. It'd be, it's close enough, right? This is in minutes. So that makes sense, right? So with a given concentration, right, initially, so initially it was 0.45 and 0.32, right? At a certain time, we found our value for K, right? And then we did another equation where we didn't know the time, but because we found the value of K in the other one, we could plug this in. We assumed 1 molar. So then 90% of 1 molar is 0.90, but we want to know what's rest of the reaction, right? So it's 0.10. So it'd be E. Oh, that's close enough to E. Yes. Okay. Any other questions you guys want to go over?
Okay, can I go back to module 5?
Yeah, that's fine.
Question 5.
Question 5, module 5. This is going to be an hour-long video. I'll cut it out. Module 5, question 5?
Yeah.
Okay. It says, which of the following aqueous solutions has the highest boiling point? Kb for water is 0.52 degrees Celsius per mole or mole. Okay, so we want to find the highest boiling point. Yes. So do you remember your formula for boiling point elevation?
Is the. You just said it right, and it's positive?
Yes. So we're given a Kb, right? Okay, so then what would the formula be? Ooh, I know you guys have it in the tip of your tongue. It's I kb molal. Yes, and it's positive, right? Because it's boiling point elevation. So then again, we want delta T, which expands to T of solution minus T of solvent, right? If we move the solvent over here, it's T solvent, where the T represents the boiling point of our solvent. Yes? Okay. And then this is the boiling point of the solution. Okay? So then, what's the boiling point of our solvent?
0.52.
That's the Kb, right? The boiling point of our solvent is water, right? Because all of these, what's it called?
Yeah, they're being.
Yeah, all of these solutes are being added to water, right? What's the boiling point? What's the boiling point of water? Yes, sir. Nice. Okay. Now this will change, right? because our I would change for all of these solutions. Yes. So we want to look at what they're giving us, and they're already giving us the molality of each. Okay. Okay. So we know KB, right? Because they give it to us. Right. Okay. So it'll be our I, which I'll leave empty. Our KB, which is 0.52, right? Okay. And then molality will depend on whatever they give us, right? Okay. So they give us potassium chloride. What's potassium chloride? How would I write that equation or formula? KCl, right? So it's potassium chloride, right? Potassium has a positive one, chloride has a negative one, so they cancel out. Okay. We're given 0.3 molar. Okay, of KCl. We're given 0.4 hydrofluoric acid. What's hydrofluoric acid? HF. Okay. 0.2 molar of sodium sulfate. What's sodium sulfate? NaSO4, but we're missing one more thing. What's the charge of sulfate? Close. Two, right? Yes, that's important. Okay, and then it's 0.2 aluminum nitrate. How would I write aluminum nitrate? Aluminum nitrate. So aluminum, right? It's Al, right? And then what's nitrate? Ooh, and O3, right? With the negative one charge. So the negative one charge goes over here. What charge does aluminum have? What group is it? Okay. So if the first group is +1, second one is +2, +3. Do you see it? Yes. Okay. And then it's point. Can't be determined, which you can. Okay. So we're given molality for all of these, right? But all of these have different Van 't Hoff factors, right? Because well, some of them are electrolytes, and some of them are just covalent bonds. Covalent bonds. Yes. So then, what's the Van 't Hoff for KCl? 1, right? Oh no, not 1. It's 2, right? Because if you put this in water, the potassium and the chloride will separate. Yes, so it's an electrolyte. It's like sodium chloride, which is water, which separates into sodium and chloride ions. Yes, so this has a Van 't Hoff of 2. Okay, what would the Van 't Hoff be for hydrofluoric acid? It's 1, right? Because it's a covalent bond. It's okay. It's okay. No, you're not. You're not gonna fail. You know you got this. So it's 1 because it's a covalent bond, right? If we were to just have sulfate here, sulfate would have a Van 't Hoff of 1. Yes.
And that's
3, right? Because this would separate into 2 sodiums and 1 sulfate. Okay. And then this one, 4, right? Because it will separate into 1 aluminum and 3 sulfates. Yes. So this has a Van top of 4. Okay. So it's just a matter of plugging all these different factors into that equation, right? So if we were to find the boiling point elevation for potassium chloride, it'll be a 2 here, right, in place of I, and then 0.3 molar, which you get what?
31.2.
31.2?
Yeah.
Are you sure?
Um,
Hold on. No, I don't know if you are. Hold on. 2 times 0.52 times 0.3.
Oh,
0.312, right? Yeah.
sorry. I multiplied it times 100.
Oh, okay. It's plus 100. Yeah, yeah, okay. So in total, it will be 100.312. Yes. Okay. Now for hydrofluoric acid, it would be a Van Hoff of 1 and molality of 4. Yes. So it's just 0.52 times 4. Oh, 0.4. Whoops. Ooh, my bad. My bad, y'all. Which is 0.208, but you add 100 to it. Yes. Okay. And then for sodium sulfate, it has a Van Hoff of 3, but its molality is 0.2. So then 0.52 times 0.2 times 3 plus 100 gives us the same value, 0.312. Right? Okay. Now, if we wanted to find aluminum nitrate, right? It's the same thing, just that of 4 here and a 0.2 here. So then times 0.2 times 4. Then we have a winner. So the highest boiling point would be aluminum nitrate because, well, taking everything into consideration, it'll give you a boiling point of 100.416. Yes, so that'll be your answer. I know it's tedious. I know.